שלומך?
בסדר, תודה, מה שלומך?
טוב, ישן.
ישנת? יופי. אני ישן אחרי זה. היום, today we have a very important subject. When I say very important, I mean it's a little bit of a hard subject. Because we're going to talk about angular momentum. What we know about angular momentum, we define it as the cross product between R to P. Right? I'm going to give you like another. Okay? Okay, we can do the introduction. So this is like a cross product in classical mechanics, and it has some meaning. And its meaning in classical physics is it's a lot of the times we have some conservation of this quantity. Because by itself we don't care about what's the angular momentum of something. We care about it exactly like we care about energies. We don't care about the energy, we care about like differences in energies. We care about differences, we care about conservation of energy or conservation of momentum. In order to understand the angular momentum and how it works in the quantum physics, we're going to first need to have some mathematical foundation. So we're going to need to first move our understanding of operators from one dimension to 3 dimensions. Because it doesn't have meaning in 1 dimension, the cross product. It's like x cross x is 0. So. Then we want to talk a little about of the. So we're gonna talk about 3 dimension, 3 coordinates, and then we're gonna finish with a little bit about a rigid rotor, which I'm gonna explain later what it is, and some matrix representation. Okay, nice. So what we have X operator and P operator. This is 1D. In 3D, we have our vector operator. We can have it a hat or just a operator, and also have like a P vector operator. A lot of the time, so when we want to write this R vector operator, we can write it as X operator, Y operator, Z operator. And we can also write it as X operator I hat plus Y operator J hat plus Z operator K hat. Why am I writing I hat, J hat, and K hat? Because I don't want to write X operator X hat. It's a little bit confusing. And I also don't want to write X operator X hat, I just want to write X. And then it'll be okay, we're doing quantum physics. In quantum mechanics, X is just an operator, it's not a value. So this is a way of writing it. And same for P operator. P operator, we can write it as Px, Py, Pz. And this is the classical, but I can just add a hat and say this is the quantum stuff. Which can be written as minus IH bar dou X I hat minus IH bar dou Y J hat minus IH bar dou Z K hat, which is equal to minus IH bar and another one. Great. So, talking about angular momentum, we have it as L equals R cos P. We can. Is this a corner? No, it's not a corner. This is. I'm going to take it as obvious. So, if we want to write this expression, we can write it first as L vector is L vector operator is Lx I hat plus Ly j hat plus Lz k hat. This is equal to R cross P. So I can write it as equal to, and I'm going to write it just beneath as ypz minus zpy I hat plus zpx minus xpz j hat plus xp1 minus ypx k hat. So up until here, it looks exactly like the classical. This is exactly the classical solution. If I want to transition to the quantum solution, I add all the hats. And now it's a quantum solution. Right. Okay. We're doing a little bit more foundations to understand. So let's, for example, focus on Ly, right? What did I do? So this is, of course, our Ly. Let's write it. Ly operator. We can write it as, what is that? We can write it as minus IH bar. This is in regular space, not in momentum space. You can write it as Z operator dot X minus X operator dot Z. So this is very nice and good. What I want to do is I want to write this momentum operator not in XYZ coordinates. I want to write it as R, theta, and phi. The reason is because most of the time R is going to be constant. Most of the time R is like some fixed length. Okay. The reason it's a fixed length, I'm going to say that now, I think it's important, is because if we consider the rigid rotator, it's like a model. In this model, what we have one mass. You have one rod. It can be in 3 dimensions. The rigid part is because this is at constant length R0, and the rotator part is because this mass is rotating. A physical example that we use this model for is, for example, when you have a yeah, exactly. When you have a molecule like a bi-atom molecule, when you have one molecule, for example H2, which consists of 2 molecules, and we say, okay, the distance between the two atoms is approximately constant. They want to see how it's rotating through space. This is just like an idea for why it's important. We can do it for a lot of stuff. So for this case, it's clear to see that because R0 is a constant, all we care about is theta and phi. Hence, it's a good measure, it's a good practice to move to spherical coordinates. So, Ly operator can be written also as minus IH bar cosine phi dot theta plus cosine theta sine phi over sine theta dot phi. And this is all nice. That I'm telling you that the transition from Ly in XYZ to R theta to R theta and phi. Notice here it's not like in z direction. It's not like a vector. It's an operator. This is z operator. Great. How we transition from one coordinate system to another. So this is like somewhat of a reminder. What we're gonna do? We're gonna do it in a robust way. An easiest way to do it, and the simplest way, is just to say x is equal r sine theta cosine phi. Y is equal r sine theta sine phi. Z is equal r cosine theta. Where let's do it. R is equal to square root of x squared plus y squared plus z squared. Theta is r cosine of z over r, and phi is r tangents of y over x. And what we want to do, basically, so this is just like the change of variables. We want to move from the x and the z to the theta and the phi somehow. It's very similar to how we try to see how operators operate on a wave function, because our question is going to be basically what is. Let's see how much space I need. I need a lot of space. Our question is, what is d to the x? So we can write it as d to the r to the x, plus d to the theta d theta to the x, plus d to the phi d phi to the x. This is a well-known relation. So it's like we look how this variable changes as all the other variables.
It's general.
Mm-hmm.
It's general.
Yeah, almost. General is usually, yeah, we can call it general. We can call it whatever we want. We are physicists. Because those are constants. 1, 2, 3. Well, the three of them are constants. We can take them before the derivative. This is a constant. This is just the rate of change, right? It's constant with respect to r. Because this is how. So we want to take a derivative with respect to r, right?
Mm-hmm.
We're gonna get something. We take a derivative with respect to. Okay, we can see it's constant with
I
respect to r.
thought we would just derivate the x equal r סינוס תטא קוסינוס פי. ולפתוח את זה כאילו לפי...
Yeah, let's do it. Let's do it, and we'll see that what we get that the derivative is getting before the partial. But we're gonna see it. So we can start with and let's have it color coded because I have a lot of colors today. So the r to the x, the r to the x is equal to x over square root of x squared plus y squared plus z squared. Can you see this marker?
Okay.
Can you see?
Yeah.
I don't, if you're at home, come here. No one sees it anyway, the microphone doesn't work. And, okay. So this is just taking a derivative of r with respect to x. Now we want to replace this x with r sine theta cosine phi, and this x squared plus y squared plus z squared with r, basically. So we're gonna have sine theta cosine phi. And this is where I stop using this marker because makes sense.
Can I have it? Sure.
Okay. Okay. So, first of all, it doesn't depend on R, we can take it before, the D to D. Miracle. Okay, let's continue. Do theta to do x. This is equal to, again, to take, this is just some derivative. I actually don't want to do all the algebra because algebra is for homework. Right? You're gonna have a lot of homework. You already have a lot of homework. Cosine theta, cosine phi over r. Let's have the third one, do phi to x, which is equal to Is it written here? Yes. Minus sine phi over r sine theta. I think what I want to say before is if I take this derivative with respect to psi, I can write it like this, and then I get to move the dot psi to the x, to the psi to the r, to the other side, and then I can just remove the psi. This is another way to show its correctness. Anyways, if you plug it all inside here, what we get is that do to the x of, let's say, some function psi is going to be equal to sine theta cosine phi do r plus cosine theta cosine phi over r do theta plus minus sine theta over r sine sine theta do phi psi. So we made one change of do x to 3 other variables times psi. Great, we are having so much fun. And where z we're gonna replace with, we're gonna say that z operator is basically r cosine theta. Now we need to do everything again for dot to the z. This is horrible. I'm not gonna do it all the way. What I'm gonna say is we're gonna get equation 5. This equation of the in the spherical coordinates when we solve everything. I just wanted to give you like the general idea of how to do it. The general idea is to write down all the change of variables, use the full differentiation rule. It's not exactly the chain rule. I think it's a different name, but whatever. And then work it out. Know that z, even though it's an operator, we can write it as r cosine theta. Just operate it to everything, and keep going. A lot of work. Questions? Is it absolutely clear what you need to do? Right, because you're gonna do it. Okay, I think we are almost done with the purely mathematical framework. Now we can start talking a little bit more about the physics. And when I mean say physics, I mean another mathematical framework, but under the title of quantum mechanics. when we have commutation relation, for example, we know that we're going to write two commutation relation, Li operator, Lj operator is equal to IH bar epsilon, the Levi-Cevichan IJK LK operator, this is one. The other one is that L operator squared Li operator is equal to 0. Those are two given relations. You can prove them yourself if you want, but I'm not going to do it. This is what we usually call the algebra of, for here it's going to be the angular momentum. So algebra in the sense that how they commute with each other. The Levi-Cevichan, I'm going to write it epsilon ijk, I'm going to write it for the equations, is either 1 minus 1 or 0. Depends if I, j, k are cyclic, I, j, k are anti-cyclic, or otherwise. Basically, it means that if we have Li, Lj, we're going to get Lk with 1 or minus 1. For example, if we have Lx, Ly, xy are cyclic with z. So we're going to get IH bar Lz. If we're going to have Ly, Lx, they are anti-cyclic with z. So we're going to get minus IH bar Lz. Okay. So these two equations, we're gonna put them here to say forever. They have physical meaning in a sense that if, for example, we measure the momentum in x, we cannot measure exactly the momentum in y, like we can, but it's gonna commute. So if we first measure the angular momentum in x and then in y, it's gonna be different than if we first measure in y and then in x. However, if we measure the general momentum, like the total momentum, L squared, we can simultaneously measure another, single other direction without influence in the system.
I have a question.
Yes.
How it's possible to measure the general תן הזוויתי וגם רכיב, כאילו זה לא...
This is a great question. It's a really great question. So basically what it means is that if we know the total momentum of the system, it doesn't put any constraints on any single direction of the angular momentum.
מודדת עוצמה כזה?
Exactly, it's like yeah, it's exactly like check what is the amplitude of angular momentum. It's an exact example.
So I can know the amplitude and only one dimension.
Yes, so we can say what is the total angular momentum, and at the same time, what is projection on the x, meaning measuring Lx. However, we cannot measure simultaneously Lx and Ly, or Ly and Lz, or Lz and Lx. It's very good because it gives us some powerful tool. It gives us an option. Because it doesn't matter which one I'm going to choose, X or Z, we're going to choose Z as a principle of like, we can do whatever, which we're choosing Z and we say Z is upwards. So a lot of the time we can say that L and Lz, L square and Lz, they are good quantum numbers and they describe all our systems. So if we know L and Lz and we measure them and we can measure them simultaneously, we know the state of the system. when I say we know the state of the system, it doesn't mean that we know everything about its momentum and about the way it is, where its location. All I mean, it's like when we say, okay, when we have psi of x, y, z, we can know it exactly, this function, which gives us some, let's say, let's say we have phi of x. We know how it looks like, we know the wave, so we know phi of x, and let's say if this is phi of x, we can also know what's its Fourier transform, phi tilde of k, and say, okay, it looks probably something like this. So when I say I have all the information and it spans all the base, it doesn't mean I know exactly where it is and what its wave number, I just know how to describe the PDF. Right. I'm gonna elaborate about it in a short way.
Can you repeat what you said about the PDF?
Okay. So what I'm saying is this is good quantum numbers in a sense that if I know the L squared and LZ, if I can know what's the measurement of both of them or what's the PDF of both of them, I can span all the bases. I can describe everything. It's the same thing as saying, okay, if we have some function f of x, we can span the bases with an x to the n, or we can say it's a sum of a bn sine of a kx. Maybe here we also need, okay, we can do e to the ikx and let k be from minus infinity to infinity. So we can, it spans a bit like the Taylor series spans the bases, exponentials span the bases. Also these two can span the bases. And I'm gonna connect it to something you already know very soon. Yes?
לא נעים לי.
Okay, so we're gonna wait another 5 minutes and we're gonna get back to it. Because I'm gonna keep explaining this subject. Okay. It's an important subject. So what I'm saying is that we're gonna represent any wave function psi. Like a lot of times for the harmonic oscillator, we have one quantum number which describes the state of the system, which is n. This is for the harmonic oscillator. So if we know the energy level, we know what is the PDF of position, what's the PDF of its momentum. So n is
PDF.
PDF, probability density function.
Mm.
It's like a PDF, it's like פונקציה צפיפות הסתברות.
Yeah.
So if you know the PDF, the probability density function of if we know the quantum number, if we know the state number, this is for the harmonic oscillator. This is like an example. If we know n, we know what is phi of x, we know what is phi tilde of k, we know everything, just not knowing what's the n. We are looking at it right now.
שזה הפונקציה עבור מצב עצמי n. טוב.
If we have a superposition, for example, if we have psi is like a function of, let's say psi is 1 over square root of 2 and 1 plus 1 over square root of 2 and 2, it's also okay, because we can span the bases with those ends and we can tell everything. Perfect. Here we're going to have exactly the same thing. What we're going to do, we're going to span the bases with L and M. Quantum numbers. I'm trying to give it like a different perspective, which is maybe a little bit harder to grasp, but it's important to understand. I hope you also seen it in the lecture, the L and M of the states. Yes, okay, I understand from the earlier. Okay, so basically, this L squared, the total angular momentum is going to correspond to L, and the projection on the Z axis is going to correspond to M. Meaning that while L could be anything which is an integer from minus infinity, minus 1, 0, 1, infinity. It could be any kind of integer if we quantize the momentum.
From 0 to infinity, it's squared.
From 0 to infinity, right? It's squared. Thank you. 0, 1, 2. Great. No, thank you. It's squared. So L could be from 0 to infinity, and could be only from minus L to L. Because it's a projection, so it could be only anti-projected. Any questions so far on what is L and LZ, little m and m? Okay, great. This is great. If you understood until this point, we're in a great place. Yes. Yes, use words.
L זה הסכימה על כל המצבים האפשריים, נכון?
איזה L?
איזה L?
small L.
כן, אני מתכוונת על הקטן.
זה
ו-M זה ההטלה שלו על כל...
L. זה בעצם סך המומנטום.
סך המצבים.
סך המומנטום. עזוב איתי.
כן, סך המצבים שיכול להיות בהם.
לא.
אז לא יודעת.
L זה כמה מומנטום יש לי סך הכל. כמה מומנטום עזוב איתי יש לי.
מה זה כמה?
L is like a measure of how fast I am. It's like how fast I'm moving. What does it mean how fast I'm moving? I can be moving 5 kilometers an hour
That's
or
L1.
10 kilometers. This is how fast. This is how much total. It's like if I'm moving an Lx, this is x, and this is y. So this is Lx, this is Li, y. But if I take Lx squared plus Ly squared, taking the square root of it, this is the total speed. It's like velocity is square root of Vx squared plus Vy squared plus Vz squared, right?
And that would be L equals 1. That's, כאילו זה מצב ספציפי עבור L שווה 1. ואז מצב ספציפי אחר עבור L שווה 2 זה מהירויות שונות בצרים השונים.
I understood your question. Let's talk about the harmonic oscillator. For the harmonic oscillator, this is N represents how much energy I have.
כן.
So it's a state, but it means how much energy I have.
In this state.
Also, no, yeah, but also like how much energy I have. This represents, it's not exactly how much energy I have.
Okay.
But from here I can say I have En energy. If I'm at state 1, I have exactly h bar omega times 3 halves.
Okay.
This L represents how much angular momentum I have, but it's also a state, like this N. So here I need only one quantum number to represent everything. Here I need two quantum numbers to represent everything.
שאחד הוא אמפליטודה והשני...
הוא ההרכב. זאת אומרת, זה כמו... This is the projection, and it's like knowing V, and Vz is enough. That's what I'm saying. So if I know what's my velocity and what's my velocity in the z direction, I can describe everything. This is my claim here.
מה זה אומר לסכום על ההטלות? זה לא ברור.
לא אמרתי לסכום, אתה אמרתי לסכום.
לא אמרת, אבל אמרנו שהם זה ההטלות, נכון? ההטלה על Z?
M זה ההטלה על זה. זה כמה מתוך זה? If M is the projection of the angular momentum of the z direction, it means how much of L comes from the z direction. And up to some more. We have it? We can ask it again later.
תודה.
Okay, great. So, let's continue. Those L and M's are something we are already familiar with because we can describe this spherical momentum or this angular momentum with the spherical harmonics YLM of theta and phi. So this is exactly the same L and M. It's like magic. the connection is more. It's like it's supposed to be further explained in the lecture, and if it's not, it means you need to assume this.
איפה אתה בתרגול?
עמוד 4, למטה. Okay. Because what I've said before, that those states L and M span the basis, what I actually mean is that we can span any basis with those YLMs. And this is any basis where we take R to be a constant. We saw...
Like you have spherical symmetry.
Mm-hmm.
Yes, exactly. We have spherical symmetry.
Like
Yes, for the R-axis. Yes, the R-axis is constant. So a lot of times what we say, we say that as a psi of R theta and phi is equal to some function R of R times YLM of theta and phi when we're doing those questions specifically. And we say this is some constant, so we don't care about it. We can just ignore it. Because when R is R0, this is some constant. So all the information of the system depends on these spherical coordinates. Okay, it's important. I'm taking it slow because it is hard to grasp, especially when you just start. Okay.
Okay.
So I can write psi of theta and phi. I can write any function of theta and phi as a superposition of L goes from 0 to infinity, of M goes from minus L to L, some constant ALM, and then YLM of theta and phi. So this is still classical stuff, in some sense that they just span a basis with a function that can span a basis. What we're going to write it, we're going to write that our state, psi, our eigenstate is going to be just this is L equals 0 to infinity, L from minus L to L, A, L, M, L, M. So state can be represented as superpositions of N and M.
Just making sure. You assume that R is a constant.
Yes.
And so you put it inside the ALM.
Exactly. When we apply those operators, so I said this is those operators relate to those quantum numbers or quantum states. How do they relate? They are so those are eigenstates or eigenvectors for those eigenfunctions for these operators. Meaning, if we operate L squared on some state L and M, we're gonna get, this is a squared operator of course, we're gonna get h1 squared L, L plus 1, nicer, L plus 1, L, M. Similarly, if we're gonna write a Z on L, M, we're gonna get h bar M, L, M. Nice. Meaning, those are actual observables. I'm going to use a lot of different words until you're going to get more and more comfortable. This is an observable. I can measure it. I can measure, when I measure this total angular momentum, I'm going to get h bar squared L plus 1 at the same state. If you're going to measure the projection over the z direction, we're going to get h by n. Does it make a little bit more sense now? Just a little bit is fine. You don't need to be.
Yes, a little bit.
A little bit is great. So what we had, we introduced some operators. We moved them to the spherical coordinates because we assume r is some constant. Right. Even if it wasn't a constant, we can solve the. We can use the separation of variables and solve the YLMs and the R, what I showed you before, separately and then multiply. I told you that similarly to sine of x and exponential polynomials, we can spend the full basis with those spherical spherical harmonics, spherical function. And I spent the basis, and I said, and I told you that if we apply those operators for those states, we're going to get some eigenvalues. Now it's going to get a little bit more interesting. So when you finish text, we can continue.
I'm not texting, אני פותחת את GPT. אני צריכה חיזוק.
It's good. I always recommend everyone to use as much of ChatGPT as you can. I use it, I learn from it a lot. But also make sure you know that ChatGPT is not a professor. I'm also not a professor, also can talk nonsense sometimes. But like, also professor can talk nonsense sometimes, but ChatGPT can make talk nonsense with a lot of confidence, which I'm not gonna do probably. Hopefully. ChatGPT it's very hard for ChatGPT to say I'm not sure, but I think that, or I don't have a clue. He doesn't do it, so. But he's supposed to be very, very good at like bachelor level stuff. Okay. We're gonna talk now about raising and lowering operators. Similarly to what we have when we have the A and A dagger for the harmonic oscillator, here we can also define raising and lowering operators. How we define them is, we write L plus, so let's write it, L plus is equal to Lx plus I Ly, L minus is equal to Lx minus I Ly. This is like magic that it works so nicely. First of all, we see they are because Lx and Ly and Lz are measurable, are observables, we can measure. They are Hermitian, but here we see that L plus and L minus are not Hermitian. Because L plus dagger is equal to L minus, but it's not equal to itself. They are different from each other. So when we apply L plus, let's put it as another one, L plus on some state LL, we're gonna get h bar square root of L plus 1 minus M plus 1 Ln plus 1. So L plus raises the projection on the z direction by 1. So from M goes to M plus 1. L minus Lm is equal to h bar square root of L plus 1 minus M minus 1 M minus 1.
אפשר שאלה?
Yes.
אז המטרה באופרטורים האלה זה אם אני רוצה לבחון איך ההיטל מתנהג אם אני מעלה אותו, מורידה אותו.
It's like, so what we have some particle, some quantum particle. It has some total angular momentum, and some of it is projected onto the z direction. Maybe all of it to the z direction, maybe none of it, maybe all of it to the minus z direction. We tell it by L and M. We can alter the direction, change the direction by applying L plus. It's not going to change the total angular momentum. It's going to just change how much is projected to the z direction.
מה זאת אומרת לשנות את הכיוון?
Another way to look at it is, let's say we have something which spins, it's in some manner, somehow, it spins, and I look at it. So none of it is on the z direction right now. All is in the xy direction, and then I can look at it like this, and everything is going to be on the z direction suddenly. Just because I change how I look at it. So one way to look at it, to say it, is we look at it differently, or we rotate the particle somehow. Because it's hard to grasp, because it's not like velocity where we can say the particle moves this way or that way. It's a cross product, classically speaking, it's a cross product between the r vector to the to the p vector. So like it's a cross product between the momentum and the r vector. So it also matters what is the from where you are looking at it. Like when we had classical physics and we looked at it from this from this coordinate or of system, or when we looked at it from itself.
Okay.
So here we had zero angular momentum. Here we had something.
Okay.
So yeah.
תודה.
So it's a concept which is a little bit hard to grasp, I know, but it is what it is. We're gonna survive. Okay. Notice that we know that M, let's put it, you can say it, okay, that M is between minus L to L, right? So what happens if we apply L plus on the state M and L? What are we going to get? I'm going to wait for an answer. Either a yes or... Let's say this is, sorry, L on M, comma, what did that what? Sorry, L, comma, M is equal to L. What are we going to get? When sorry?
M יעלה באחד.
So you want to say we're going to get L and L plus 1?
Wait, but the eigen...
כן, לפי התבנית כאילו פה ב...
No, but the eigenvalue would be 0.
Exactly. We're going to get 0. Because we cannot have...
כי הוא בגבול העליון.
Exactly. Because we cannot have more angular momentum projected to the z direction than what we have in general. So if we put it here, M is equal to L, we're going to see we get here Itzik minus Itzik, which is 0. On the other hand, if we had lowering operators on L and M equals minus L, we're also going to get 0. Because if you put here minus L, we're still going to get Yerucha minus 0. Things that all more?
No.
That's all I know. So did you understand? That's all I can say. Okay. It's good. It's good we're doing it a little bit slow today. Because it means it's a good subject when it's a subject. A little bit of, let's have another definition. It might be useful for you in the future. We call, and this is how we call, because we call the L When L is equal to 0, we call it singlet. When L is equal to 1, we call it triplet. The singlet, the states which are allowed for the singlet is just a single state, 0, 1. For the triplet, we can have 1, 1, 1, 0, and 1, minus 1. So if you hear the word singlet and triplet, this is the reason. Here we have 3 triplet, and we have 1 singlet. It's not something you need to have deep understanding. Just like something.
That should be 0, 0 in the signal.
No.
No.
Yes, of course. Thank you.
Yeah.
Yes, I make a mistake. I told you. You hopefully don't make nonsense stuff. Okay.
No, good.
It's good. Okay. Let's see what we can erase and what we're going to need later. This might be here. Let's do it like this. Now we're gonna get to talk about the rigid rotator. So after we had some motivation, what I'm gonna do is I'm gonna give some general explanation. It's more of a motivation, it's not a proof. For why? For the rigid rotator, we write the Hamiltonian as L squared over 2I.
So it's called in Hebrew.
Which one?
רוטור קשיח?
כן. אבל...
סיבוב מקובע.
לא משנה, יאללה, סתם.
It's something which is doesn't change its values and rotates in 3 dimensions. So we can. So the reason why we do it is because we say that we don't have a potential. We have just a constraint that R is a constant, and usually H is equal to like T plus V, where T is the kinetic energy, V is the potential. Here we say we don't have potential, so we have T, and we say is that T is equal to, and we say this is equal to P squared over 2M.
What is the capital I there?
It's the moment.
Yeah.
It's inertia moment.
Okay.
Thank you. So exactly. So we say okay. So we have that L is equal R cos P, but R is a constant in R hat. And we can write, and we can let ourselves believe that we can write P as L over R naught. And we can write also that I, the inertial moment, is equal to M R naught squared. And here we have, so we can continue the algebra and get that this is equal exactly to L squared over 2I. With those assumptions. This is just the easiest way to explain why we get this Hamiltonian, and we consider it a rigid rotator way. We also can say that it doesn't depend on R, like it doesn't have any, it is a symmetry in R, spherical symmetry, because R is a constant. Okay, I'm gonna write this part. Let's write it a little bit bigger. So if we try to apply this H to some state L and M, what you're gonna get? You're gonna get E, L and M, L and N. Right? This is all well known. For us, if we take the definition of H, I'm gonna have 1 over 2I, L squared L comma M. It's gonna be equal to 1 over 2I, H bar squared L plus 1 Lm. Therefore, our energy, which is dependent only on L, will be equal to 1 over 2I H bar squared L plus 1. Something which is very important to note is that we have a degeneracy, nivum, of the energy, meaning we get the same energy for different states. Those are all the states M equals minus L to L. So because the energy doesn't depend on M, we have a degeneracy. We have the degeneracy nivum, degeneracy is equal to, I think it's 2L plus 1. Exactly. So we have 2L plus 1, which is all the, corresponds to M equals minus L plus 1, 0, 2L. Do we understand the meaning of the degeneracy? Okay, we're very happy. Let's do an example. Yes! Let's do an example! Woo! Let's do an example. So we have a rigid rotator. It's not rotator, it's water. And so we have a rigid rotor. We assume we know the moment inertia, and that's its wave function psi of theta and phi is equal to some normalization constant. I have to call it n and tilde for normalization times cosine of 3 theta. What's the first thing we do? Okay, so the question is, we want to find, so we have two questions. One is to find the probability of being in some Lm state. Two, we want to find the average energy. So first of all, what we need to do, we want to find the normalization constant. This is the most important thing. And we know, let's assume, not let's assume, I know that the normalization is exactly 1 over 2 square root of 35 over 17 pi. The reason I know it is because what I'm doing in the homework is I'm going to check that an integral that psi is going to be equal to 1. The brief idea of how to do it is I'm going to integrate over all the spherical coordinates, psi conjugate psi. Here the conjugate is just itself. Which is just an integration from 0 to 2 pi d3, integration from 0 to pi d theta sine theta and tilde square cosine squared over 3 theta. And we try to find which n gives us 1 for this integration. Questions of how to normalize in spherical coordinates. Wait.
How do I solve this integral? How do I solve this integral?
Yeah, this is algebra. You can look at it later. So our question is, what is the probability to be at some state L and M? We want to find the probability. We want to find the probability to be at some state L and M. Meaning, when we write psi, we can write psi like this.
And then
So
ALM squared.
what we want to know is what is ALM. If you know what ALM, this is equal to ALM squared. So basically we want to span this function as a summation of all the modes.
We do like projection and all.
Yeah, we can do projection. We can write that this sum is equal to n to the cosine 3 theta. Then integrate over all space with respect to like add a summation with like L tag, M tag to the integration. But we're not gonna do it. This is something you should never do in an exam, also in your homework, because you can do it a lot easier. How? So, if you like in one of the first lectures we did something which is very similar. We're gonna do the same. We're just gonna look at the first spherical coordinates. Specifically, I'm gonna give you 2 spherical coordinates we're gonna use. Let's write it over here. We can use y10 of theta and phi is equal to square root of 3 over 4 pi cosine theta, y of 3 and 0 theta and phi is equal to, and then 5 cosine cubed of theta minus 3 cosine theta. And we can use those 2 definition of y1 and 0 and y3 and 0 to describe this wave function. So this is exactly the L and M. This is like what we have here is basically 1, 0. And what we have here is 3, 0. So because we have cosine, we have cosine of 3 theta, we can use some trigonometric relations to find it as an expression of cosine to the third and cosine to the first power.
I believe.
Yeah, we're gonna do it. We are gonna do it together. So we can write this as n tilde 4 cosine cube of theta minus 3 cosine theta. This is some identity. Usually you're gonna have those identities in the test or in homework, and if you don't, you can just Google it up if you're doing homework, or go to the toilet and Google it up if you're doing an exam. And no, not really. And yeah, you can start working. And when we walk through the algebra, we get that psi of theta and phi, which is the eigen state psi, is equal to, and including the normalization and all, is equal to minus square root of 21 over 85 1 0 plus 8 square root of 1 over 85 3 0, where this is y1 0 and this is y3 0. I'm trying to skip the algebra so you will be able to sit here during this tutorial and think of how we're going to do it, to have like an overview idea. So what we do, we first, when we have cosine of 3 theta, we're going to like expressions of cosine or sine of only theta. Then we try to express it as YLM. And then we basically are done. So one is only like calculate the projection. We can go through this relation with the sums, but we are not going to do it. Like almost never going to do it because it's going to be very hard. I think I did it in my exam because I was stupid back then. But I got a good score. So we're not that. No, I think I started and then I switched in the middle to just oh, I know what it is. Okay. So the probability to be at this state is going to be the coefficient squared. The probability to be in this state is going to be this coefficient squared. And for any other state, the probability is going to be 0. And if you take this coefficient squared plus this coefficient squared, we're going to get 1. Exactly. What is the average energy? What is E?
You do the simple like sum of probability of Ln times the energy of L, which is actually energy of L.
We can write it as L equals 0 to infinity. M is equal minus L to L. E L M B L M L M, and then we need to actually write it as, so when we have E, ignore what I wrote here, so when we have E, I can write it as psi E psi. So I need to have two sums over L1 and 1, L1 M1, A L1 M1, E L1 M1. It doesn't matter which E I choose, if I choose L1 or L2. And then we're going to have another two sums. L2 equals 0 to infinity, M2 is equal minus L2 to L2, then L2 M2, sorry, then A L2 M2 L2 M2. I'm doing it the crazy way on purpose, just so you won't be scared. But yeah, so we can clearly see that if L1 is different than L2, because it spans the basis, it's orthonormal to each other, so L1 must be equal to L2, L1 must be equal to M2. So we can, and then they destroy each other after, as this is a constant, this is a constant, and this is a constant, so we can take them outside. So we get basically a sum over L, let's say L1, from 0 to infinity, a sum from M1 from minus L to L, and we can write it as A L1 M1 squared, E L1 M1. Then I can write it for the L1 M1, L2 L, and now L2 must be L1 M1, which is equal basically to 1.
Could AL1 M1 be complex?
Could? Yes, of course. We have here like you're right. Here we have a conjugate because it's the M1. Questions?
שואלים A יכול להיות מורכב?
כן, A יכול להיות מורכב. AL1 M1 צריך להיות, כאילו A בכללי יכול להיות מורכב. So AL1 M1 can be complex number, complex coefficient. Here we need to take the conjugate. So here we have an absolute value. This is because this is because psi is equal to psi conjugate.
נדבר. אני...
Here we know that for basically E is only depends on L. We know it from here. So this is all equal to, and we know that AL1 M1 is 0 for anything but L equals 1, M equals 0, and L equals L equal 3, M equals 0. So we're gonna have A1 0 E1 plus squared absolute value plus absolute value of A3 0 squared E3, where this coefficient is A10 and this coefficient is A30. You know what I did here is a little bit complicated. I complicated even though it's not in the tutorial, the notes, because I think it's important to understand also how it works rigorously. Because you can tell me, okay, Omer, I know that because I can say that the average energy is also equal to sum over all states I, the probability to be at a state I times the energy in this state I. You can also write this energy like this, so we can say, okay, we have only two possible states. This is the probability. This is A1, so we can write it as we have only two states, and we can write the probability to be at state. The first state is going to be A10 squared times E1 plus the probability to be the second state, possible state, is A30 squared E3. This is what I would write in the text. I wouldn't write everything like this. However, I want to connect to what we did so far in the course and why it should work. Doesn't matter. We can do it rigorously or out of a little bit of intuition and practice. It's the same exact solution.
שאלה, אם זה חופר מדי, אז תגיד לי, נדבר על זה אחר כך. הרי אנחנו מדברים על כאילו חלקיק שקורה לו משהו, זאת אומרת יש לו סך אנרגיה סופי כלשהו. איך קורה שיש אלים שונים. אל מייצג, כי אמרנו שמסתכלים על זה בצורות שונות.
זה כמו חלקית באוסילת ההורמוני, זה אותו דבר.
איך יש אנרגיות שונות?
רגע, זה הגיוני לך שבאוסילת ההורמוני אני יכול לעשות חלקיק אחד ויהיה לו אנרגיות שונות?
הסופית הכוללת שלי.
סכום, אתה יכול לתאר את זה בתור סכום על הרבה מודים. להגיד יש לנו סופר פוזיציה, בין הרבה מודים שונים, שהם החלקיק יכול להיות באוסילת ההורמוני. יכול להיות כזה גם ברמת אנרגיה ראשונה, גם בחמישית וגם ב-26. גם פה, אותו דבר, יכול להיות להתחיל באיזשהו סופר פוזיציה. היה לנו שיחה כיפית. Questions before I erase everything. You don't have enough questions, you need to ask more.
Oh, okay.
If you don't ask more questions, I'm gonna be very mad. In China, you don't ask questions, but in Israel, you ask a lot of questions. It's fine, it's good. This is how we learn. We are more rude. Feel free. You don't have to ask questions, but feel free to ask questions. Okay, we're gonna have now we're gonna continue something we did last time in some sense, but in the spirit of angular momentum. Last time we started talking about finite energy systems. Here we're gonna assume that L is equal 1.
זה דף תרגול אחר?
Same. Page 7. So for L equals 1, we're gonna have the states 1, minus 1, 1, 0, and 1, 1, where I remind you it's L, comma L. In this form, in this framework, we can write our operators Lz and x and y and L squared as matrices, finite size matrices. So we're gonna start by representing this as. I can represent this. Let's be consistent. Let's see what we should here. So let's write here minus 1. And this is 1. I can represent this vector as 1, 0, 0. This one as 0, 1, 0. And this one as 0, 0, 1. I can do it in a lot of ways. I just did it in one specific way to make it easier for me and for us. Great. We want, for example, to write an L squared operator such that when I apply it, we want to write it as a matrix, and it's going to be a 3 by 3 matrix. So when I apply it to the 1, 1 state, I'm going to get h bar squared. That's right. When I apply it at L squared to 1, 1, I want to get what? H bar squared 1 plus 1. H bar squared times 2. 1, 1. If I apply it to 1, 0, what I'm gonna get? 2h bar squared 1, 1. Because it doesn't depend on L.
Yes.
Depends only on the total argument. And if I apply it to 1, minus 1, I'm gonna get this is not 0. 2h bar squared 1 minus 1. So I can just tell you that what we have here, the matrix operator is going to be 2h bar squared 1, 1, 1, 0, 0, 0. 0, 0, 0. I can just tell because if we apply it to this vector, because it's like, it doesn't matter, it's gonna be the same eigenvalue for all the vectors, and they are diagonal, so it's all nice. But there's like a way to do it more carefully. The way is to say, okay, when we apply an operator to an initial state, we get some value times the final state. And we can write this L operator as a sum over all final. I'm gonna write it final. So if I what I said, I can find L squared to initial and state and get the final state. And I can write it, have here some constant if I want, let's say A. So I can write L squared as a sum over all A final initial. Then you can just multiply by the initial, by the bra of the initial on both sides. Because this is for a specific state, this is for, and I can write here all states. How it translates to this picture, I can write L as a sum over here. It's going to be a sum over, and I can take let's say that L squared over 2h bar squared, just to take it outside. But from here I'm going to get 1, 1, 1, 1 plus, from here I'm going to get 1, 0, 1, 0, 1, 0 plus 1 minus 1, 1 minus 1. Those are all the identity matrices. No, it's not identity matrix. So what we have here, we're going to give it a little example. So here we're going to have 1, 0, 0 times 1, 0, 0. This is this part, which is going to give us 1, 0, 0, 0, 0, 0, 0, 0. Okay, look confused. I'm going to give another example. From this multiplication, from this inner product, I'm going to get 1 in the middle, and 0 is outside, and from here I'm going to get 1 at the bottom right, and 0 is on there. So what I have here is basically the identity matrix. Let's have another example, or you have a question regarding this example? Let's have another example. Let's write that. I'm going to do almost the same example now. Now I want to write the matrix form of LZ. Let's do it in red because it makes a split from the inside by this point. LZ for 1, 1 is going to give us h bar 1, 1. LZ for 1, 0 is going to give us 0. And then Z for 1, minus 1 is going to give us minus h bar 1, minus 1. So using, let's say, some operator. Final initial, where LZ is operating on the initial states and gives us a final state. Meaning I call this part the initial, and this part, including the coefficient, final. So I can write LZ as, let's do final initial h bar 1, 1, 1, 1 initial plus 0 minus h bar 1, minus 1, 1, minus 1. Let's write it, up until here it makes sense, okay. Let's write it in vector form. You have h bar 1, 1, it's gonna be 1, 0, 0 times 1, 0, 0 minus h bar 0, 0, 1, 0, 0, 1. This is equal to h bar. This product gives me a 3 by 3 matrix where everything is 0 but the first term. And this gives us another 3 by 3 matrix that everything is 0 but the last term. Overall we get h bar 1, 0, 0, 0, 0, 0, 0, 0, minus 1. It makes sense because if I operate it on the first eigenstate, I get h bar times m, which is 1. On the second state, m is equal to 0. So I get 0, nothing. For the third one, m is equal to minus 1. So I get minus h bar, or h bar times minus 1. I have more stuff, but I think we are done. I think we are not capable of continuing. You can go a little bit over the end of the lecture notes if you need some more practice, and you're gonna have enough homework also. And feel free to reach out to me. I basically live in this building, but not next week. Next week.
תודה.
תראה בהרצאה שלנו.
תראה במה?
בכנס.
איזה כנס?
שבוע הבא לא פה, אני בכנס. את רוצה עכשיו שנשאר?
וואלה, יש לי תכף עוד תרגול.
בסדר,
אז אני קצת טובה. מתי אתה הולך לכנס?
פשוט כל שבוע הבא לא פה. קל.
האוניברסיטה משלמת?
משלמי שלנו.
מתרגש?
עצוב שתקוי.
לא, זה נשמע נחמד.
הייתי מעדיף לא ללכת הפעם. הפעם, ספציפית.
איפה זה בגרמניה?
אני מוכן להחליף אותך. רק תגיד לי מה לומר.
לא,
אתה בטוח את כל השיעורי בית?
כן, אני מבקש הערכה, אני רוצה גם